In a world where innovation and scientific advancements lead to a better future, few understand many beginnings arise from federally funded research that initially seemed obscure or strange. The Golden Goose Award will explain the stories of some of these influential researchers that have helped shape the future for a better tomorrow.
Who is Dr. Charles Towns? Well, that's one of the most interesting things. He's many different men. He's had 3 or 4 different iconic careers. Most people know about the laser.
The rumor is that he invented the wetsuit.
The Navy asked me to form a committee to study how to get to shorter wavelengths, and we had this committee and we met and we just didn't discover anything. But I got up early in the morning worrying about it. And breakfast wasn't ready, so I went and sat on the park bench and thought, now why haven't we been able to get the shorter wavelength? I thought, hey, wait a minute. We can get more molecules in the upper state than the lower state, and then they can amplify. Oh, how? Now, many people thought it wouldn't work. And in fact, the head of the department and the previous head of the department, both of whom got Nobel Prizes in physics, so they weren't stupid people. They came to my lab and said, look, that's not going to work. We know it's not going to work. You know it's not going to work. You've got to stop. You're wasting the department's money. Well, fortunately, I was an associate professor then. They couldn't fire me just because I was dumb. So I said, no, I think it has a chance of working. And about 4 months later, we had it working, of all things.
So the laser work evolved when Towns came to Berkeley, and he went and measured ammonia molecules in space. And then in the 70s, he started using CO2 lasers, and so these are now the world's highest frequency radio telescopes. And we're trying to resolve surface features on nearby stars using a laser-based interferometer.
Money is supplied by a lot of different kinds of groups, but the government has the biggest batch of money of anybody, and the government has supported research, and it's a good thing. I used federal funding. The federal funding was just for general support of the study of atoms and molecules, of all things. And out of that then came the maser and the laser, which then do have a lot of applications. That's the way of support of general science, to support science, and you learn a lot of things. Every once in a while something has terrific applications, and it helps our industry a great deal and helps our economy a great deal. I'm now 97, and life is such fun, I like to keep going. I want to live, make it at least to 100, we'll see. It's fun to learn new things and discover new things.
There was a marine biologist at Penn State who was looking at marine animals, particularly sea urchins or coral, and what their basic structure was. And using the imaging technologies that Dr. Gene White had, they were able to see that the structure of these materials was a very uniform calcium structure, that 50% or so of this was the calcium, and the other 50% was empty space.
If you looked at a block of the material and you were shrunk to a very tiny size, you would be able to enter at any point, any hole in the thing, go anywhere in a structure and come back out anywhere. So it was completely interconnected. It
was translational research as a project, and there were NIH funds that went in to look at some of these applications in blood vessels, artificial trachea, or the other work that continued was to use these also as an artificial bone substitute.
I brought an interest to it from a basic crystal chemistry standpoint. In other words, I was trained as a chemist, a material scientist, to convert this material to something that's more useful.
Having the right pore structure, tissue can then ingrow it and secure it, and that's a critical component of, like, artificial joints. How do they connect?
The calcium phosphate compound that we made is identical pretty much to the hydroxyapatite mineral that's in your bone.
When you look at these pieces of coral, the pore sizes there were big enough that it really worked in as a bone implant, and currently that technology moved along to a commercial company and still is on the market, and there's been, I don't know, hundreds of thousands or even millions of patients that currently have been treated or have this as a bone substitute. No one knew exactly what the value was or what it would translate to, In sort of summary, it's supported not only into biomedical and current implant materials, but other basic information and, you know, related to just how that porous structure could be used.
So in 1989, I heard a seminar that very much changed my life. In this seminar, work by one of my other co-laureates, Osamu Shimomura, was described about this protein from jellyfish called green fluorescent protein, or GFP. And since at the same time I was working on a small animal that was transparent, that we could do genetics on, and that we wanted to know where genes were being activated, I realized that if we could have those genes activate the production of this green fluorescent protein, all we would have to do is shine blue light onto the animal and we would see where the genes were because they would turn green. The third person to share the Nobel with Osamu and I was Roger Chen. Roger has contributed enormously to the improvement of GFP and made it really a much more workable tool.
We needed to start making different colors, not just because I love pretty colors, but because there was a biological need to see several proteins independently all at the same time, and if they all came out different colors, that would be the easiest way to go. We also happened to need to have these two colors talk to each other in a special way.
And you cannot predict what part of basic research is going to be the answer to disease.
When you genetically put GFP into HIV, it now glows green. So many of our hopes for a vaccine were that we could give a vaccine to sick people after they've already got AIDS. What a vaccine means, it provokes the patient to make antibodies, and antibodies are outside cells. But if this virus doesn't ever have to go outside, then those antibodies won't have a chance. Seeing that the virus can jump from one cell to another without going outside, that was entirely dependent on making the virus glow green.
Metastasis of cancer. Being able to watch things in living tissue is exceptionally important, and I think it has changed a lot of how we view developmental biology, neurobiology, genetics, and cell biology. Scientific research is an investment in the long run. It's not something that you say, if we do this experiment or if we do these things, then this will occur. Scientific progress is a cumulative effect, but what's absolutely essential for that is basic research. And you cannot predict what part of basic research is going to be the answer to this disease or this condition or whatever. One needs to have a very broad base. And I think in the United States, there has been a wonderful support of science. One sees a real flourishing of scientific discovery and all the subsequent changes that ensues. Benefits in the life of people, new medical procedures, improvements in agriculture. But that required a long base. A great number of Nobel Prizes for these wonderful discoveries that have been made. But without that base of basic research, we really can't do the applications. And we are nowhere near of understanding enough to say, oh, we're done with basic research.